Chapter 22, Alcohols, Ethers, Phenols, and Thiols. We're going to cover a bunch of different functional groups this chapter. So again, a functional group is a group of atoms of an organic compound which give it specific characteristics. And as we saw earlier, alcohols are a type of functional group. There's an OH coming off of your carbon group. That makes it an alcohol. It has a hydroxyl group. And if the hydroxyl group is coming directly off an aromatic ring, like this benzene here, that makes it a phenol. So alcohols, ethers, and phenols are structural derivatives of water. They have that OH just like water has. So we see water has this OH here. You're just changing, for an alcohol, one of the H's to an organic group. With an ether, you switch both hydrogens for organic groups. And in ether, you have the OH again, but now you have an aromatic ring coming right off of it. Models illustrating the structural arrangements of these atoms in methanol and ethanol. So here's methanol. You see in black is carbon. Hydrogen is in white. Oxygen is in red in this schematic. And here we see our OH group coming off of our methyl group, methanol. Ethanol, eth, 2 carbons, and then anol, because it's an alcohol. We have ethanol. So methanol, meth for the one methyl group, and then anol for the alcohol group. Methanol, ethanol. If there's 3 carbons, propanol. 4 carbons, butanol. 5 carbons, pentanol. 6 carbons, hexanol. 7 carbons, heptanol. 8 carbons, octanol. Primary alcohols. Your OH group is coming off of a primary carbon, which means it only has one other bond to organic substances and 2 H's. Secondary alcohol is coming off of a secondary carbon. That carbon has 2 organic groups bound to it and 1 hydrogen. And a tertiary alcohol is coming off of a carbon that is bound to 3 other organic groups. So it's a tertiary carbon. So whether an alcohol is primary, secondary, or tertiary is dependent on what type of carbon the OH hydroxyl group is bound to, if it's primary, secondary, or tertiary. So here's different types of structural formulas for 2-butanol. The line structure, again, 2. The OH is coming off of the second carbon, 2-butanol. Polyhydroxy alcohols. These are alcohols that have more than one OH group. And these include diols, triols, and carbohydrates like D-galactose and D-glucose. And so here we're looking at galactose and glucose, and we see lots of OH groups coming off of them. Many, many, many OH groups found in the carbohydrates. So practice problem. Each hydroxyl group in a polyhydroxyl alcohol can be classified as primary, secondary, or tertiary. So let's identify each of them. This carbon, this is a secondary carbon because it has 2 bonds to different carbons and just 1 hydrogen. The next one's also secondary. This one here is secondary. This one here is secondary. And this last one, this is a primary carbon. It's bound to only 1 other carbon group and 2 hydrogens. So we have 4 secondary carbons and then 1 primary carbon for the OHs to attach to. IUPAC rules for naming alcohols. We first select the longest continuous chain of carbon atoms containing the hydroxyl group. And then we number the carbon atoms in the chain so that the OH group is on the lowest possible numbered carbon. So when you're picking what side to start numbering from, you pick the side that puts the lowest number on the carbon with the OH group. And then from the parent, to get the parent alcohol name, take off the E from the alkane and get all. So propane becomes propanol. Methane becomes methanol. Ethane becomes ethanol. So we have 1 propanol. The OH is coming off of carbon number 1, right there. 2 propanol, that's isopropanol, that's like rubbing alcohol. The OH is coming off of the secondary carbon in the middle there. Here we have cyclohexanol, 1,3-cyclohexane diol, because we have 2 OHs, it's a diol. 3-methyl-1-butanol, we get the longest chain, has 4 carbons. And you want to make sure the OH is on the lowest numbered carbon, so this becomes carbon 1, and you have a methyl group off of carbon 3. And 1,2-ethane diol. Again, the diol means there's 2 OH groups. So practice problem. Name the following alcohol using the IUPAC method. Well, let's find the longest carbon chain. We got 1, 2, 3, 4, 5, 6, 7. So we see 7. So 7 is hepta. So we're going to have a heptanol here. And now if I start counting from this way, 1, 2, 3, 4, OH would be on carbon 5. If I start from the other end, it would be 1, 2, 3. It would be on carbon 3. 3 is lower than 5, so this is the correct end to start numbering. So it's going to be 3 heptanol, and I see on carbon 5 I have 2 methyl groups. So we have 5,5-dimethyl, 3 heptanol. Again, we started numbering from this side because that put the lowest number on the OH group. And then at carbon 5 we had 2 methyl groups, so that's dimethyl. 5,5-dimethyl 3-heptanol. Write the structural formula of 2,4-dimethyl 2-hexanol. Well, let's start with hexanol. We know we have 6 carbons to work with, so we draw them out. And we know that it's 2-hexanol, so the OH group is coming off of carbon 2. And then 2,4-dimethyl off of carbons 2 and 4, we add methyl groups. So first we put our 2-hexanol down, and that's just 6 carbons in a row with the OH group coming off of carbon 2 because it's 2-hexanol. And then we add the 2 methyl groups. So 1 methyl group at carbon 2, 1 methyl group at carbon 4 to get 2,4-dimethyl 2-hexanol. Alcohols, again, contain a polar hydroxyl group. And the OH group undergoes hydrogen bonding, which increases the boiling point of alcohols compared to corresponding alkanes. So whereas methane is a gas, methanol is a liquid. Ethane was a gas, ethanol is a liquid. Propane was a gas, propanol, rubbing alcohol, is a liquid. Butane was a gas, butanol is a liquid. And that's due to the extra hydrogen bondings between the O's and H's in this alcohol. Because we remember hydrogen bonding can occur between a protic hydrogen and nitrogen, oxygen, or fluorine. That was in chemistry 1. This polar group gives increased solubility of alcohols in water compared to the corresponding alkanes. And so methanol, ethanol, and the propanols are completely miscible with water. Once you have 4 carbons, only T-butyl alcohol, the tertiary butyl alcohol, is miscible with water. 2-butanol, about 10% of it will dissolve in water, but it forms 2 distinct layers at that point. So as the alcohols get bigger, there's enough carbons where it's no longer water soluble. But the really tiny alcohols, methanol, ethanol, and then propanol and isopropanol, are completely miscible with water. They mix with water easily in one layer. So the boiling point of an alcohol is much higher than the parent alkane, and this difference is because of hydrogen bonding. And we look at the boiling point of the alcohol, it's about 100 degrees higher than the alkane that it came from. Solubility. Alcohols with 3 carbon atoms or fewer are infinitely soluble in water. As we said, ethanols, methanols, and propanols are all infinitely soluble in water. And once you have 4 or more carbons, you start losing water solubility. if you add more OH groups, that increases water solubility. So 1 hexanol, only 0.6 grams, will dissolve in 100 grams of water. But D-glucose, again, 6 carbons, hexanol has 6 carbons, and glucose has 6 carbons, but instead of just one OH functional group, I have a ketone here, or an aldehyde, because it's a terminal, it's at the end with the H, so that's an aldehyde. And then I have 1, 2, 3, 4, 5 OH groups, and that rapidly increases water solubility. So we see that 95 grams of D-glucose will dissolve in 10 grams of water. So that, let's times it by 10 again, and you get 950 grams of glucose dissolving in 100 grams of water. So it's much, 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 much more soluble. And even at home, you can do this. 50% sugar and 50% water is how you make simple syrup, and it's used in different cooking recipes. But when someone's making simple syrup at home, it's really just equal mass of water and sugar. And sugar, sucrose, like glucose, is very soluble in water because of all those OH bonds. Branched chain alcohol. These, if the carbons branch out, if they're not in just one long chain, but they start branching, this lowers the boiling point. It makes the molecule more compact and has less area over which intermolecular forces can act. So for example, 2-butanol is branched and has a boiling point of 91.5 degrees Celsius, whereas 1-butanol is straight chain and has a boiling point of 118 degrees Celsius. So the more branched the alcohol gets, the lower the boiling point will be. So list the alcohols in order of increasing boiling point. Well, methanol is the smallest. It's going to have the lowest boiling point. Then propanol, and then butanol, and then pentanol. None of these are branched. They're all linear, and so we're just going by size. 1 carbon, 3, 4, and 5. Alcohols undergo many reactions, including these 5 major ones. You can protonate the OH group to form the oxonium ion, the OH2+, which is useful because that's a good leaving group. And so something like a chloride or a bromide can slam into that carbon and displace off of a water. And so a lot of times you have to use a little bit of acid with alcohols to form the oxonium ion if you want to convert the OH into a good leaving group. You can deprotonate the OH to O-, and now you have an alkoxide which can attack other things. We can oxidize the alcohol into an aldehyde or a ketone, or we can oxidize an aldehyde all the way to a carboxylic acid. We can dehydrate an alcohol to form an alkene or an ether, and we can esterify it to form a carboxylic ester. So acid-base properties of alcohols. It's a weak acid, it's a weak base. It's a weak acid because this hydrogen can pop off, but it's like water. It doesn't really do so very much. And it's a weak base. It can grab another proton, but it's not good at doing it. So you need a pretty acidic solution for that to happen. So if you want to add another H+ onto that oxygen, you're going to have to add some acid to catalyze that reaction. Base properties of alcohols, with the formation of oxonium ions in the presence of a strong acid. So here, you put in sulfuric acid, and that's a strong enough acid, though, even though methanol is a weak base, it'll grab that proton. So those electrons will attack this proton to form the oxonium. And now this can do a lot of chemistry because something can slam into this carbon and you can kick off that water because that's a neutral molecule if it leaves now. And so this is a good way to convert an OH group from a bad leaving group because OH- will never be kicked off of a carbon in a nucleophilic reaction, whereas the H2O definitely can. So this is a very common practice of activating your OH group so that it becomes able to leave so we can do chemistry. Acid properties of alcohols. Formation of alkoxide ions in the presence of strong bases. If you have a really strong base, you can remove this hydrogen to get O-, the alkoxide. Common way to do that is use pure sodium metal, because as this oxidizes to Na+, you'll release hydrogen gas and you get the alkoxide. So this is sodium ethoxide. And now this negative charge is pretty active and it'll attack things. The order of reactivities of alcohols with alkali metals is the primary alcohols are the most active, then secondary, and then tertiary. Oxidation. The oxidation state of carbon is determined by the functional group. Aldehydes, ketones, and carboxylic acids are more oxidized than alcohols. And so, primary alcohols are oxidized to aldehydes and then further oxidized to carboxylic acids. Aldehydes are actually more reactive than alcohols, so you need to use a special poisoned catalyst if you want it to stay at the aldehyde range. With a normal oxidizer, it'll go right to carboxylic acid. Secondary alcohols, these are oxidized to ketones. The tertiary alcohols are not oxidized because you're not going to break the carbon-carbon bonds there. So oxidation. Here's a breathalyzer, and we use chromium salts so to look at a color change in the ethanol dichromate reaction. This is not a super accurate test, and so this is what's called a field test. And so a police officer will have somebody pull over on the side of the road and blow into it. And if they fail this test, then a person would actually go to a police station and then blow into a much more sophisticated infrared machine to really test how much alcohol is there. And so this is useful and convenient chemistry, but it's not accurate enough to be legally definitive, which is why there's a much bigger, much more accurate and calibrated machine in a police station as opposed to these handheld tests. But they operate based on the oxidation and reduction of the dichromate ion. So, metabolism of ethanol. Ethanol is oxidized in people's liver if they drink alcohol. Too much ethanol is toxic. So here ethanol is oxidized to acetaldehyde, which is ethanal. Aldehydes get AL endings. And again, excessive alcohol consumption will cause cirrhosis of the liver. Too much alcohol too often is physically bad for people. This acetaldehyde, or ethanal, is further oxidized to acetic acid, which is a natural product that you find in the body, and now it can be eliminated. What are the products when 2-butanol is oxidized? Well, this is a secondary alcohol, so the furthest we can oxidize it is to a ketone. Again, to oxidize it further, you'd have to break a carbon-carbon bond, and that's extremely unusual, so that doesn't happen in this class.